Hello there and welcome to Group 20A's wing design presentation. We're here to talk you through the design process we took when designing an aircraft wing for an aircraft of particular specification. So, as well as being the correct length, our wing has to survive a particular torsional load and a particular bending moment, which means it isn't allowed to twist more than 5 degrees and it isn't allowed to break under the bending moment we place it. So we begin our journey at the chalkboard as we create a conceptual design for our spar. So our main concerns are: what material do we have to work with? What shape do we want the spar to be? How do we minimize the weight of the spar in total? And how can we construct it? What tools do we have? Now, the only material available to us is foam board and in limited supply. So I think before we consider any more design specifications, we should give this material a quick test and see how it behaves. So we built an informal test spar and found that the sides tended to buckle before the entire structure broke under tension. Next, we considered how small we could actually make the spar and whether or not this would fit inside the rib or whether we would have to cut the rib around it. And how do we deal with the issue of the buckling sides? Perhaps we could thicken the walls of the spar, but if so, how do we deal with the added weight? Perhaps if we taper the spar, we can cut some of that weight off. That would also have the added benefit of allowing the ribs near the wing tip to fit more comfortably. Now we have to consider if we can actually build the spar with the tools at our disposal. We will have to glue large lengths of spar quickly before it dries. The thin parts at the tapered end of the spar will be very prone to breaking if we're not careful. We can't waste the material because we have such a limited amount, so every piece needs to count. We also must cut everything by hand and be careful not to cut ourselves. Now we enter the preliminary design stage, where we use our trusty spreadsheet based on existing theory about structures to create the smallest possible spar geometry we can, without causing the spar to fail, which for us means keeping the direct root stress lower than both the ultimate compressive and ultimate tensile stress, along with keeping the angle of rotation below 5 degrees. Once we've got our geometry set, we can go about creating a detailed design in SolidWorks to see if our assembled wing would actually work. Now that we have accepted a design, we need to build it and test it to find out if it performs as predicted, by adding weights to the tip and recording the point at which it breaks, which will be this spar's ultimate bending moment. Initial testing gives the ultimate bending moment at 5.49 Newton meters compared with the predicted value of 3.3 Newton meters. This is likely due to the foam board being stronger than expected. So we head back to our preliminary spreadsheet and adjust the foam board strength values based on our experimental results. We can now update our spar geometry, making it even more lightweight. And so we entered a cycle of building new spars, testing them and feeding the information back, repeating until we were eventually happy with one to build our final wing around.